Welcome back to Cosmos in a Pod, Space and Astronomy series.
Hmm.
Today we're taking a deep dive into something truly mind-bending.
Yeah.
Black holes,
Yeah.
those regions of space-time where gravity is so strong that
Wow.
nothing, not even light, can escape.
Exactly. It's like a cosmic trapdoor
Oh,
where
wow.
the pull is so intense it warps the very fabric of reality.
That's a great image. So how do these cosmic enigmas form? I
Right.
mean, where does a black hole even begin?
Well, you might be surprised to learn that many black holes are born from
Really?
the death throes of massive stars.
Okay, that makes sense, sort of. But what makes a star massive in this context? Is it just
Yeah.
any old star that's bigger than our sun?
Not exactly. We're talking about stars at least 3 times the mass of our sun. To
Wow.
give you some perspective, that's like comparing a grain of sand to a boulder.
Oh, wow.
These stars live fast and die hard, ending their lives in a spectacular cosmic display.
So walk me through this stellar life cycle.
Mhm.
How does a massive star
Okay.
go from shining brightly to becoming a black hole?
Let's imagine a massive star burning bright in its prime. This is its main sequence phase.
Okay.
It's fusing hydrogen into helium in its core, generating immense energy that pushes outwards, counteracting the inward pull of gravity. It's a cosmic balancing act.
Like a cosmic tug of war.
Exactly.
Gravity pulling in, fusion pushing out.
Right.
But what happens when the star starts to run out of hydrogen fuel?
That's when things get really interesting. As the hydrogen dwindles, the star starts fusing heavier elements like helium and carbon in a desperate attempt to keep the energy flowing.
Huh.
This causes the star to swell up into a red supergiant hundreds of times larger than its original size.
So it's like the star is puffing itself up,
Exactly.
trying to stay alive.
But this strategy has its limits. Eventually, the star's core becomes predominantly iron, and iron is a cosmic dead end. It can't be fused to release energy.
So what happens then? Does the star just fizzle out?
Not quite. Without the outward push of fusion energy, the core collapses under its own immense gravity, and this collapse triggers one of the most powerful explosions in the universe. A supernova.
Wow, that's got to be a sight to see. What happens during a supernova?
Think of it as a star's grand finale. The outer layers of the star are blasted into space with incredible force, spewing out heavy elements that will eventually seed the formation of new stars and planets.
So even in death, a star gives back to the universe. That's pretty amazing. But what happens to the core of the star after the supernova?
Well, that's where things get really interesting. The fate of the core depends on its mass. If it's below a certain limit, it becomes a neutron star, an incredibly dense object made almost entirely of neutrons.
Okay, so a neutron star is super dense,
Yes.
but not quite a black hole. What's the tipping point? What pushes it over the edge into black hole territory?
It's all about gravity. If the core's mass exceeds a certain limit, about 3 times the mass of our sun, which is called the Tolman-Oppenheimer-Volkoff limit,
Okay.
gravity becomes unstoppable.
So this limit is like a cosmic weight limit for a dying star's core.
You could say that. If the core is heavier than this limit, gravity wins the ultimate tug of war. The core collapses further, squeezing itself into an infinitely small point called a singularity.
Hold on. Infinitely small. Doesn't that
Yeah.
defy logic?
It does seem counterintuitive, but that's the nature of a singularity.
Yeah.
It's where our current understanding of physics breaks down. At this point, the density becomes infinite, and the gravitational pull becomes so strong that nothing, not even light, can escape. That's when a black hole is born.
Whoa. So it's not just about size, it's about density and this extreme warping of space-time. But what about the edge of a black hole? The point of no return. What's that called again?
That's the event horizon. It's the boundary around the singularity beyond which escape is impossible. Once you cross the event horizon, there's no coming back.
So the event horizon is like the ultimate cosmic barrier, and the singularity is the heart of the black hole where everything gets crushed into oblivion.
That's a great way to put it.
This is all so mind-boggling. And we've only just begun to scratch the surface of black holes, haven't we?
Right.
I mean, we've been talking about these stellar mass black holes, but aren't there supermassive ones out there too?
No, absolutely. Supermassive black holes are millions or even billions of times more massive than our sun. They lurk at the centers of galaxies, including our own Milky Way. Their formation is still a bit of a mystery, but it's thought that they might grow over billions of years by swallowing up stars and gas, or even merging with other black holes.
So these supermassive black holes are like the ultimate cosmic heavyweights shaping the galaxies they inhabit.
Exactly.
Welcome back. So we've established that black holes are out there,
Yeah.
warping space-time and
Mm.
potentially swallowing anything that gets too close.
Right.
But here's the thing that blows my mind.
Yeah.
How do we even know they're there?
Right.
They're called black holes for a reason.
Yeah. That's a great question. It's a bit like a
Yeah.
cosmic detective story where we have to look for clues and piece together the evidence. Black holes don't emit light that we can see directly,
Wow.
but they exert a powerful gravitational influence on their surroundings.
So we're playing cosmic detective, looking for their fingerprints on the fabric of the universe.
Exactly.
How do we do that?
One way is by observing the motion of stars.
Okay.
If we see stars orbiting a seemingly empty point in space
Oh,
at incredibly high speeds,
wow.
it's a strong indication that there's a massive unseen object pulling on them, a black hole.
Ah. So it's like watching a dance where one partner is invisible, but you can tell they're there by how the other partner is moving.
That's a fantastic way to put it. And the faster those stars are whipping around,
Yeah.
the more massive the hidden black hole must be. That's how we figured out that there's a supermassive black hole at the center of our own galaxy, the Milky Way.
That's both amazing and slightly terrifying.
Right.
So their gravity is one clue.
Right.
Are there any other ways we can see the invisible?
Yes. Another clue comes from the material that falls into a black hole. As gas and dust get sucked in, they form a swirling disk
Oh.
around the black hole called an accretion disk.
So it's like a cosmic whirlpool with everything spiraling down the drain.
Exactly. And as this material gets closer to the black hole,
Okay.
it heats up to millions of degrees,
Wow.
emitting intense radiation, including X-rays.
Hold on, you said nothing can escape a black hole.
Right.
How can we see radiation coming from them if light can't even escape?
That's where it gets tricky. The radiation we detect isn't coming from inside the black hole.
Okay.
It's from the superheated material in the accretion disk, just outside the event horizon.
So it's like seeing the glow from a fire, but never actually seeing the fire itself.
Precisely. By observing these X-rays and other radiation, we can study the properties of the black hole, estimate its mass and spin, and even get glimpses of the chaotic environment around it.
That's incredible. It's like we're piecing together a puzzle, using these indirect clues to understand these cosmic behemoths. Is there anything else we can learn from the radiation coming from these accretion disks?
Yes, the radiation patterns can tell us about the black hole's spin. If the black hole is spinning rapidly,
Oh, okay.
it can actually drag the fabric of space-time around it, creating a sort of cosmic whirlpool that affects the radiation emitted by the accretion disk.
So it's like the black hole is stirring the pot of space-time, and we can see the ripples in the radiation.
That's a great analogy.
You know, for something that's invisible, we sure have learned a lot about black holes.
Right.
But even with all this detective work, I imagine there's still a lot we don't know.
You're absolutely right. Black holes are still shrouded in mystery. For example, we still don't fully understand what happens to the information that falls into a black hole.
Yeah, that's the information paradox we touched on earlier. It's like information goes in, but
Yeah.
then what?
Right.
Does it just disappear?
That's the big question. It seems to violate one of the fundamental laws of physics, the idea that information cannot be destroyed.
So physicists are scratching their heads over this.
Yeah.
Are there any potential solutions on the table?
There are some fascinating theories out there. Some scientists believe that information might be encoded
Oh.
in subtle correlations within the black hole's event horizon, or even radiated back out
Okay.
in a scrambled form through a process called Hawking radiation.
Hawking radiation.
Yes.
Tell me more about that.
It's a theoretical prediction by Stephen Hawking that black holes aren't completely black after all,
Oh.
due to quantum effects near the event horizon.
Bunkers.
They actually emit a faint radiation.
So even black holes can leak a little bit.
Exactly. And this Hawking radiation could carry away information about what fell into the black hole, potentially solving the information paradox.
It seems like the more we learn about black holes, the more mind-blowing they become. Are there any other cutting-edge areas of research that you're particularly excited about?
Definitely. One of the most exciting developments in recent years is the ability to detect gravitational waves, ripples in the fabric of space-time that are produced by cataclysmic events,
Oh.
like black hole collisions.
Wait, we can actually detect these ripples in space-time. How is that even possible?
It's an incredible feat of engineering and scientific ingenuity.
Wow.
We have these incredibly sensitive observatories like LIGO and Virgo
Right.
that use lasers to measure tiny changes in the distance between mirrors. When a gravitational wave passes by, it stretches and squeezes space-time, and these observatories can pick up those minute changes.
It's like we've built giant ears that can listen to the symphony of the cosmos.
That's a beautiful way to put it. And by studying these gravitational waves, we can learn about the masses and spins of the black holes involved in the collisions,
So cool.
providing us with an entirely new way to probe these enigmatic objects.
So it's like listening to the echoes of these cosmic clashes, revealing secrets about the black holes that created them.
Exactly, and this is just the beginning. As we develop more sensitive instruments and build new observatories,
Okay.
we'll be able to detect even fainter gravitational waves, opening up a new era of black hole astronomy.
Wow, it seems like we're on the cusp of some truly groundbreaking discoveries. But before we get ahead of ourselves, I think we need to take another quick break. We'll be back soon to wrap up our deep dive into the mysteries of black holes. Welcome back to our final segment on black holes. You know, for a long time, these objects were seen as purely destructive,
Right.
like cosmic vacuum cleaners, just gobbling up anything in their path.
Yeah.
But as we've been exploring,
Yeah.
the reality is far more nuanced and fascinating.
Indeed. Black holes are not simply about destruction.
Okay.
They play a surprisingly constructive role in the universe as well.
Okay, so spill the cosmic tea. How do these seemingly destructive forces actually contribute to the growth and evolution of the universe?
One key aspect is their influence on star formation. Remember those supermassive black holes at the centers of galaxies? Well, they can actually act as regulators, preventing galaxies from becoming too hot and forming stars too rapidly.
Wait, I thought black holes were all about sucking things in,
Right.
not pushing them away. How does that work?
It's a delicate balance of energy. As material falls into a black hole, it gets superheated and releases immense amounts of energy.
Yeah.
This energy can heat up surrounding gas clouds and push them away, preventing them from collapsing and forming new stars.
So it's like a cosmic thermostat,
Exactly.
keeping things from getting too hot and chaotic in the stellar nursery.
That's a great analogy. And it's this kind of feedback loop that helps galaxies evolve over billions of years, shaping the grand structures we see in the universe today.
That's incredible. It's like these black holes are playing a cosmic symphony, orchestrating the birth and death of stars across vast expanses of space.
Exactly. And let's not forget about the heavy elements that black holes help to spread throughout the universe.
Oh,
Remember those jets of material we talked about earlier? Well, those jets can carry elements forged in the intense environment around the black hole,
interesting.
out into the galaxy, enriching the interstellar medium.
So those elements, the building blocks of planets and life, are essentially the ashes of stars that were consumed by black holes.
In a way, yes. It's a beautiful cycle of cosmic death and rebirth, where the destruction caused by black holes ultimately contributes to the creation of new stars, planets, and even the possibility of life itself.
That's pretty poetic when you think about it. From cosmic monsters to cosmic gardeners, black holes really are multifaceted
They
objects.
truly are. And the more we learn about them, the more we realize how much we still don't know. There are so many fundamental questions that remain unanswered.
Like what? What are some of the biggest mysteries that are still out there?
Well, for one, we still don't fully understand what happens inside a black hole at the singularity. Our current laws of physics break down there, and we need a new theory of quantum gravity to truly grasp what's going on.
So it's like peering into the abyss, and our current understanding just doesn't quite reach that far.
Exactly. And then there's the information paradox, which we discussed earlier. Does information truly get lost when it falls into a black hole?
Right.
Or is it preserved in some way? Solving this paradox could revolutionize our understanding of the very nature of reality.
It seems like black holes are not only cosmic enigmas, but also gateways to some of the deepest questions in physics and philosophy.
I couldn't agree more. They challenge our understanding of the universe and push us to explore new frontiers of knowledge.
As we wrap up this deep dive, I'm left with a sense of awe and a renewed appreciation for the vastness and mystery of the cosmos.
It's been a pleasure exploring these mind-boggling objects with you.
And a huge thank you to you, our listeners, for joining us on this cosmic adventure. We hope you found it as fascinating as we did. Don't forget to follow and subscribe to Cosmos in a Pod, and check out our YouTube channel for more deep dives into the mysteries of the universe. Until next time, keep looking up and stay curious.